Hey guys, Miss Burns here. I'm very excited to get back to some normal stuff and do some series with you guys again. So we're getting towards the end of our chapter on series, and we've got a couple more tests that I want to go over. So section 9.5, we get into what's called alternating series. We've done a little bit with alternating series, but now we're going to learn a formal test that we can use whenever we have an alternating series to see if the series converges. So up until now, for the most part, I think earlier in the chapter we might have looked at some terms that, or some series that included terms that were both positive and negative, but most of what we've done has only included terms that were positive. So an alternating series is one whose terms alternate in sign. Generally they go from positive to negative. So for example, this would be called an alternating geometric series, because if you think about when n is 0, this would be a positive term. When n is 1, this would be a negative term. When n is 2, it would be a positive term. And then when n is 3, negative. So it would go back and forth between a positive term and a negative term. Oftentimes, we see an alternating series. It could be written this way, but a lot of times we'll see it written this way, where they'll put the -1 to the n power in the front. Sometimes it'll say n plus 1. It depends on what this n value starts at, depending on whether they want it to start with a positive term or a negative term. But this -1 to a power in the front, and then the rest of the series after it, that's a good indication that you're working with an alternating series. But as soon as you see that the signs are changing, you're working with something that's alternating. So this would be the terms 1, -1/2, 1/4, -1/8, and so on. And so, by the way, you see that was geometric because 1/2 to the n would be a geometric series, but because of the alternating, we'd call it an alternating geometric series. So the alternating series test for convergence tells us this. So as long as a sub n is greater than 0, so let me back up for a second. What do I mean by a sub n? A sub n is the part without the alternating. So in this previous example, the a sub n term that they're talking about would have been the 1/2 to the n without the -1. So the positive part right here, ignoring the negative for a second. That's what they mean by a sub n. Okay, so if it's written this way, or like I said, it could be written this way with an n plus 1 term, but either way, just looking at a sub n, that's the part that's positive. That will converge, so the series will converge if two things happen. If you take the limit of a sub n as n goes to infinity and it goes to 0, that limit approaches 0, and if the sequence is decreasing. So in other words, the a sub n plus 1th term is always less than the a sub nth term. So in other words, the 5th term is less than the 4th term. The 10th term is less than the 9th term. The 1000th term is less than the 999th term, and so forth. So you have to show that it's a sequence that is decreasing the entire time. If those two things are met, if those two conditions are met, then that tells us that the series is a converging series. The original alternating series that we dealt with is converging. Let's do an example. To determine the convergence or divergence of this series, this is called the alternating harmonic series. If you remember, right before spring break, we mentioned the p-series test, and the most basic p-series is 1/n. That was called the harmonic series. You may or may not remember. Well, you should remember. We talked about p-series. If p, remember, is less than or equal to 1, right? So just 1/n is all I'm looking at right now. We said that that diverged. So the regular harmonic series would diverge. But the question is, what does the alternating harmonic series do? So now this is alternating because of this -1 in the front. So let's check those two conditions we just talked about. First of all, if we take the limit as n goes to infinity of just a sub n, which in this case is 1/n, that gives us 0. So that first condition of the test is met. The second condition, remember, is that the sequence itself for 1/n has to be decreasing. As n gets large, are the terms themselves getting smaller and smaller? Well, one way to think about that is to set up a little inequality and say, okay, the n plus 1th term, a sub n plus 1th term, would be 1/n plus 1. The nth term would just be 1/n. Is this always a true statement? And if the numerator is a constant like 1, this is usually a very easy comparison to look at. Do you agree that 1/n plus 1 is always going to be less than 1/n as n gets larger and larger? And yes, you should agree to that, because this denominator is always going to be a little bit bigger than this denominator, which means this fraction is always going to be smaller than the fraction that came right before it. So the two conditions for the series are met. It is a decreasing sequence, and the limit of the sequence goes to 0. So we can conclude that the alternating harmonic series back here converges. How about this one? Determine the convergence or divergence of this alternating series. So we can tell it's alternating because of this -1 raised to a power. This is our a sub n term right here, n squared over n cubed plus 1. So let's first start with taking the limit. So we want to take the limit as n goes to infinity of that sequence. And you can use L'Hopital's rule if you want to, but remember we talked about comparing the degree of the numerator to the degree of the denominator when you have a rational fraction like this. And so because the denominator is a larger degree, that means the whole thing is going to go to 0. Now the question is this a decreasing sequence? Now you notice that this numerator is not a constant like it was in the previous example. So in the previous example, the numerator was a 1, right? Like here, we were able to compare these pretty easily because the numerators were constant, and all we had to deal with were the denominators. In this example, it's not quite so straightforward because we've got a numerator that has a variable in it. So one way to think about this is to think about it as a function instead of a sequence. So if we look at the function x squared over x cubed plus 1. Think back to calculus 1. How did we tell when a function itself was decreasing? Remember back in Calc 1, this was like the first half of the semester. If we wanted to know where a function was increasing or decreasing, remember, we always looked at its first derivative. And we looked at the behavior of the first derivative. Or not the behavior, I should say. We looked at the signs of the first derivative. If the signs were positive, remember, the function was increasing. If the signs were negative, the function was decreasing. So let's look at the derivative of this function. So I'm going to take the derivative using a quotient rule. I think I probably did a little algebra to clean this up here, but I want you to pause the video and go through the quotient rule. The derivative of the first times the second recopied minus the derivative of the second. And then all over the second function squared. If we simplify and clean this up, I'm going to end up with this expression right here. So when is this expression going to be negative? Well, all right, like I said, the denominator is always positive because it's being squared. So the question is, this will be negative whenever the numerator is negative. Okay, so look at the numerator. The numerator, the way I've written it, is x times 2 minus x cubed. X is always going to be a positive term by itself. Why is x always a positive term? Well, go back to what we were looking at. Our series starts at n equals 1. So I only care about values that are larger than 1. So x we know is going to be a number bigger than 1. So we know this first part is always going to be positive. So when will this numerator be negative then? When the second factor, 2 minus x cubed, is negative. So I'm going to solve this little inequality here. Add the x cubed and take the cube root of both sides. So let's just kind of summarize this. This is negative, this derivative is negative whenever x is larger than the cube root of 2. Well, the cube root of 2 is a small number, it's like 1 point something. So the point is, as x goes out to infinity, or as n goes to infinity in my sequence, this derivative we know will be negative, which means this function will be decreasing. So our series will be decreasing as long as n is greater than or equal to 2, because remember our n values are all positive whole numbers. Since it's the long-term behavior that we're interested in, and that's what tells us whether a series converges or diverges, we can now say that this is a decreasing sequence in the long run. And so both conditions of the alternating series test are satisfied and our original series converges. We're not going to get too crazy with these functions. This one was, I just wanted to show you an example of one where you could look at the derivative of the corresponding function and determine whether the function itself was decreasing. And if the function's decreasing, so too is the sequence. And so that meant the second condition was met. Determine the convergence or divergence of this series. Okay, so let's take a look at the two conditions for the alternating series test. The limit as n goes to infinity of n over 2 to the n minus 1. By the way, look at how I wrote this. I took this negative out. So this could be written as -1 to the n minus 1 power times 2 to the n minus 1 power using properties of exponents. So the negative is not really what's important here. We want to look at the limit of this sequence as n approaches infinity. So what's going on here? we could use L'Hopital's rule if we want to, and if we use L'Hopital's rule, we get 1 for the derivative of the numerator. The denominator, we did exponential functions back in chapter 5. The derivative would be the natural log of 2 times 2 to the n minus 1, and that limit, of course, would be 0. However, if you didn't use L'Hopital's rule, it's not a big deal. In fact, you should be able to tell me this limit is 0 without using L'Hopital's rule by looking at growth rates. Remember, we've talked a lot about growth rates. Which of these grows faster? Is it the numerator, which is a polynomial function, or the denominator, which is an exponential function, right? Hopefully you're thinking exponential grows faster, which means the entire fraction grows smaller. So the first condition is met. Now we need to look at the series and see whether or not the series is decreasing. So we're going to do the same thing I did in the last example. We're going to look at the corresponding function. The derivative of this function, here it is using a quotient rule again. So the derivative of the first, of course, is 1 times the second recopied minus the derivative of the second, using that exponential rule derivative, times the first recopied all over the second squared. We want to know where this would be negative. Here it is again. All right, so similar to the last example, this denominator will always be positive. So it's really the numerator that we're interested in. I factored out, little algebra here, I factored out the common factor of 2 to the x minus 1. So that left me with 1 minus x times the natural log of 2 in parentheses. Now 2 to the x minus 1 is an exponential function. Can you visualize an exponential function? You can put it in your graphing calculator if you want to. It's an exponential function that's shifted to the right 1 unit, but it will always be positive. Exponential functions, unless they have some kind of reflection, are always positive. So that leaves us what's in parentheses. So when is that negative? Well, if we set that inequality up and we attempt to solve for x, add the x to the natural log, x times natural log of 2 to the other side, divide by the natural log of 2. In other words, whenever x is greater than 1 over the natural log of 2, which is some small decimal, we have a positive, or we have a decreasing function because this expression would be negative. And that number is about 1.44. So as long as the corresponding function, if we're looking at the corresponding function whenever x is larger than about 1.44, we can say that means our series is also decreasing as long as x is greater than or equal to 2. So just like the last example, in the long run, the function, or the series itself, is decreasing. The limit of that series went to 0, so we can say this passes the alternating series test and therefore converges. Let's try this one, the convergence or divergence of this series. So we have negative 1 to the n, that tells us that it's an alternating series, times 3n over 4n minus 1. So start with the limit of the sequence, 3n over 4n minus 1. Now right away, you should look at this and you should be able to say, okay, you can either think of it as L'Hopital's rule or just think about it as growth rates. These are growing at the same rate. So the limit, remember, will be the ratio of the leading coefficient, which is just 3/4. What does that tell you? That tells you that the limit doesn't approach 0, which means the first condition of the test fails. Now, one thing I want to point out about the alternating series test is it's a test for convergence. So I would not say it diverges by the alternating series test. What we need to do is verify, and this does diverge, but we need to verify it in some other way. So we can also just fall back to the nth term test. Remember the nth term test for divergence? That was the very first test we learned in this unit. And we can say, okay, what is that limit? Remember we said if that limit is anything other than 0, this diverges. And that's the case we can use here. Even though it's an alternating series, we can still say that it diverges by the nth term test. Alternating series remainder. So one more topic that's important with series that are alternating, and we're going to use this as a really important skill, so put a star by this. We're going to use this again in the next unit because we're going to see alternating series again, is the remainder. So remember, let's talk about what all this means. S is the infinite sum. S sub n is the partial sum. So I have the infinite sum of a series, and then I have its partial sum. So let's say I only add up the first 15 terms. The difference between the actual infinite sum and the partial sum would be what we call the remainder of the infinite series. So the absolute value of this remainder is always bounded by the nth plus 1 term that I stop on. Here's what I just said again in words. the remainder from approximating an infinite sum S by using a partial sum is always bounded by the next term of the series. And this would be used if we need to approximate a sum or get a range for how good our approximation is. This is a very common technique. Let's do an example. So let's put some numbers with this. I think this will help clarify. Approximate the sum of the series by using the sixth partial sum. So we have an alternating series, an infinite alternating series, and we don't know what the actual infinite sum is, but we want to approximate it by using the sixth partial sum. So that would be the sum of the first 6 terms. So first, let's verify that this actually does converge using our new alternating series test. First, you're going to look at the limit as n approaches infinity of 1 over n factorial. Of course, that goes to 0. And then you're going to look at the n plus 1th term compared to the nth term. How does the 1 over n plus 1th term compare to the 1 over nth term? Well, we can see this denominator is going to be larger than this denominator, which tells us it's a decreasing series. And so the two conditions are met. For the alternating series test, we know it converges. Now let's actually find the sixth partial sum. Okay, so what I'm doing is I'm physically writing out the first 6 terms. So the first term would just be 1, right? Because the series starts at n equals 1, so 1 over 1 factorial would just be 1. The first term is positive because if n is 1, we have an exponent of 2 here, which makes the first term 1. So 1, the next term will be negative, 1 over 2. Third term will be positive, 1 over 6. Where is the 6 coming from? Well, 3 factorial, right? For the third term would be 3 times 2 times 1. The fourth term would be 4 factorial. 4 factorial, 4 times 3 times 2 times 1 would be 24. Fifth term would be 5 factorial. Notice the signs are alternating, so that's 120 for 5 factorial. And the sixth term would be 6 factorial, which is 720. If I put all that in my calculator and I add it up, I get an approximation of 0.63194. So what we want to know is how good is our approximation. I don't know what the actual infinite sum is. Remember we said there's not, unless it's a geometric or a telescoping series, those are really the only two, other than a few special ones out there, that we actually know the infinite sum for. So we have to approximate the infinite sum using these partial sums. And the question is, how good is my partial sum approximation here? We know that the remainder between the partial sum and the infinite sum is bounded by, so from that theorem you just wrote down on the previous slide, this remainder right here is bounded by the next term from where I stop. So if I added up the sixth partial sum, the next term would be the 7th term. Let me show you what I'm talking about. So the remainder using my sixth partial sum is bounded by a sub 7, which is literally the 7th term. So the 7th term is 1 over 5,040. Where am I getting 5,040 from? That would be 7 factorial. Put a 7 in here, 1 over 7 factorial. Put a 7 up here, this becomes a positive term. So my 7th term is 1 over 5,040. That means my approximation is this close right here to the infinite sum. It's a pretty good approximation. My approximation is within 0.002 of the infinite sum. So that means my approximation is either under or over the actual infinite sum by this amount. So our infinite sum lies between 0.63194 minus that number and 0.63194 plus that number. So the actual infinite sum, even though we don't know what it is, we know that it lies between these two boundary points. Okay, I've got one more piece to this video. I promise I'll go quick here, but I want to talk a little bit more about a concept called absolute versus conditional convergence. It sounds like those are big terms. They're really actually not that bad. So we're still talking about alternating series, of course, and here's sort of the logic behind these two definitions. If we take this series, for example, this is the alternating harmonic series, 1 over n, remember, is the harmonic series. We said a few minutes ago, earlier in the PowerPoint, so go back, I think this was maybe the first example we did, that we said that this series converges. However, if we take away the alternating part and just look at the regular harmonic series, 1 over n, remember, based on p series, we said that diverges. So what that means is we would say the original series, the alternating series, converges what we call conditionally. So in other words, this series converges on the condition that it includes the alternating part. Now, on the other hand, if we look at this series, so this is a geometric series. I think we actually did this one earlier in the PowerPoint, and we said that this converges using the alternating series test. We could go through and we'd show that. But without the alternating part, this still converges, right? Because it's a geometric series with a common ratio of 1/2. So if the series converges with or without the alternating, we say it's absolutely convergent. So that second example is an example of a series that's absolutely convergent. Because if I take away the alternating part, it still converges. If the series only converges when it's alternating, then we say it's conditionally convergent. In other words, it alternates, or it converges on the condition that it alternates. So, for example, oh, my phone's talking to me. For example, let's look at this. So, all right, so let's write this down. This is a theorem that kind of sums up what we just said. If the absolute value of a series converges, so if the series converges without the alternating part, the absolute value of the series converges, then we say the original series that's alternating converges absolutely. If the series converges, but the absolute value of it diverges, then we say that the alternating series is conditionally convergent. So make a note here of these two examples. So the first statement there, the absolute convergence statement, that's the second example I just showed you. The conditionally convergent statement, that's the first example I just showed you with the harmonic series. If the series, the absolute value of the series converges, then the series itself that's alternating will also converge. This theorem simply tells us that if we can show the absolute value of an alternating series converges, then that's good enough to show that the alternating series also converges. Let's do an example. Determine whether the series is convergent or divergent, and then if it's convergent, classify it as either absolute or conditional. Okay, sorry about that. A little technical issue. All right, so let's take a look at what's going on here. So we want to know whether or not this is converging or diverging. So the first thing we want to do is see if we can apply the alternating series test. So hopefully you observe that if we take the limit of n to n factorial over 2 to the n, as n goes to infinity, which of these grows faster? Remember, we talked a lot about growth rates. Here they are again. Which of these grows faster? Remember, we said factorial is like the Superman function. It beats everybody. So this numerator is going to grow faster than this denominator, which means the limit does not equal 0. It goes to infinity. So we could say that this diverges by the nth term test. So if you see that that limit doesn't go to 0, you can say it diverges by the nth term test, even if it's an alternating series, and be done with it. Okay, let's look at this series. So we've got cosine n over n squared as n goes from 1 to infinity. This does include positive and negative terms, because if you think about cosine values, those can be positive or negative, but it's not technically considered alternating. And if you think about how the n values would affect this, if n is 1, you'd have cosine of 1 radian, which would be in the first quadrant, some value, but it'd be in the first quadrant, which cosine would be positive. Cosine of 2 would be in the second quadrant, which cosine would be negative, but then cosine of 3, if n were 3, would also be in the second quadrant. So it's like you would go positive, negative, negative, then you'd get to the third quadrant, have negative value, negative, then back to positive. So it's not really alternating in the sense that it doesn't alternate in signs. You have sometimes positive, sometimes negative, but they don't alternate back and forth. And so what we could do to figure out what's going on here is let's look at the absolute value of this series, because remember what that theorem said a few minutes ago. If the absolute value of the series without the alternating part, without looking at negative terms, if that converges, then we can say the whole thing converges absolutely. So n squared is always positive because I'm squaring a term, so I'm just going to put the absolute value in the numerator. And then what I'm going to do is I'm going to do a comparison test to the p series 1 over n squared. So what I want you to think about, first of all, what does 1 over n squared do? N squared, 2 is your p value, so that would converge, right, using the p series test. So absolute value of cosine of n over n squared is always less than or equal to 1 over n squared. Why? Why is that true? What do you know about your cosine values, your cosine and your sine values? they're always between 1 and -1, -1 and 1, -1 and 1. They're always in that range. So this numerator, the absolute value of this numerator, is always going to be less than 1. And so what we could say is that this series converges by direct comparison to this p series 1 over n squared. So since the absolute value converges by direct comparison test to the 1 over n squared, we can say that our original series also converges, and it does so absolutely. Determine the convergence or divergence of this series. So now we have an alternating series, -1 to the n over the natural log of n. So let's check to see if the alternating series converges. So the limit as n goes to infinity is 0. So the first condition of the alternating series test holds. And then how about the second condition? And the reason this test is convenient to use is because it's easy to compare these two fractions because the numerators are constants of just 1. So 1 over the natural log of n plus 1 will always be less than 1 over the natural log of n as n goes to infinity, because this denominator will be larger than this denominator. So we know that this series converges by the alternating series test. However, we want to know if this converges absolutely or conditionally. So let's go back and let's look at the original series without the alternating part, and let's see what happens. So the series without the alternating part would just be 1 over the natural log of n. How can we look at that series? What could we use? Well, I'm using a direct comparison to the harmonic series 1 over n. The harmonic series 1 over n, remember, diverges. So which of these denominators is going to be larger, the n or the natural log of n? Natural log of n is always going to be slower in growth than n, so 1 over n is going to be a smaller fraction than 1 over the natural log of n. So if 1 over n diverges by direct comparison, 1 over the natural log of n has to also diverge. So what does that tell us? The alternating series converged using the alternating series test, but the absolute value of the series diverged using a direct comparison test. So that means that the original series has conditional convergence.